Everybody, καλησπέρα σε όλους. Θα κάνω την εισαγωγή στα αγγλικά προφανώς. We have the pleasure of having with us Professor Allison Jaynes. Allison has received her PhD from the University of New Hampshire in USA. And after her PhD, she worked as a postdoc researcher at the University of Colorado in Boulder. And since 4 years, since 2017, she has joined the faculty at the University of Iowa. So the University of Iowa was the University of James Van Allen, and Allison will today talk about the Van Allen probe's mission. So it's a nice match. Allison's research focuses on the inner magnetosphere particle dynamics, including the ring current and the radiation belts, and how they connect to atmospheric and auroral physics. So it is consistent that she is participating in the PRESTO program of SCOSTEP, which is the 4-year scientific program of SCOSTEP, and it has 2 of its pillars are magnetospheric physics and also atmospheric influence of solar and the magnetospheric dynamics. So Allison is serving as the co-lead on the PRESTO committee for predictions of the Sun-Earth environment. And she's also a member of the AGU nomination task force and a member of the National Academy study on increasing PI diversity and inclusion in the leadership of competed space missions. That's a long title. And she has previously co-chaired the Geospace Dynamics Constellation Science and Technology Definitions team for NASA. So thank you very much, Allison, for being with us today. And you have the floor.
All right, thank you, Giannis. That was great. I'm gonna try to keep an eye on the chat. I think it'll pop up if there's a chat. But if anyone has questions while we go through, someone, bring it to my attention audibly, because I may not see it. Yeah.
Okay. So Allison, Allison, do you feel comfortable with being interrupted if there is a question?
Yes, absolutely.
Yeah? Okay, yeah. So I will keep an eye and we'll let you know.
Okay, perfect. Thank you. All right, so I'm going to talk today about some of the discoveries that we've had specifically from energetic particle observations from the Van Allen probes. And I'm going to start with a little bit of background and start very basic, and then I will move into some more complicated topics as we get towards the end of the talk. So hopefully it will appeal to both magnetospheric physicists and non-magnetospheric physicists. So I wanted to start here by showing this picture, and we're going to see kind of where this fits in a few slides. But this picture here is the energetic particle environment that exists around Earth. So just seeing this picture here, you can get an idea of the complications and complexities of what we're trying to study when we make these observations. All right, so why do we even care about what's going on up there in the near Earth space environment? So this is kind of my pitch to why this really matters to society. And I would say that one of the most important existential crises that we are facing globally is how do we deal with our modern life in the face of this impulsive sun that we live with? And you can see here in the photo that in the diagram that we have, of course, all of our space assets, technology up there in space, but we also have things that are closer to Earth and even on the ground that are affected or can be affected by space weather. So we've got transpolar flights, for example. We've got induced currents in power lines and pipelines. And so all of these things can be affected down to the ground level by these big events that we see coming from the sun. Now here in the US, we've just barely started dealing with this. There was a national space weather strategy that they came up with in 2015. And we're supposed to be enhancing our preparedness for space weather events, but it's bureaucracy, so it's slow, right? We're not even really getting to the point where we're getting some funding injected into the system for studying space weather. And that's okay, because really what a lot of us are interested in is the physics. Want to deal with the government or policy or anything. But it's good to remember that this does have an impact on society. And I would say that where we are right now is that we need to do much better. So the state of our forecasting ability is pretty poor, and we need to really ramp up if we're going to do anything like forecasting or predictability of this system. All right, so let's talk a little bit about how the solar wind kind of creates that near Earth environment. So a lot of us know that we've got essentially, it can be approximated as a bar magnet embedded within Earth, and that creates this nice magnetic field that you expect from a bar magnet. But when you add in the effects of the sun, you'll see that what looks like a simple dipolar magnetic field gets distorted. And that's from that continuous solar wind that is coming off the sun, and it changes in intensity. So there's particles in magnetic field that's coming from the sun, and it impacts the magnetic field around Earth, so that we have this long stretched tail away from the sun, and we have compressions towards the sun, and we have energy being injected into the system. We can have really explosive events happening back here in this magneto tail, and that ends up giving us things like radiation belt enhancements and the really beautiful aurora that we see down on the ground. So how this looks in a cartoon format here is you'll see all these overlapping plasma regions, right? But the general shape here is one of this stretched tail, and I like to make the analogy to a windsock, this kind of weather tool here, because the solar wind really does blow the magnetosphere around. So you get a lot of flapping, and you get this sort of wagging of the tail of the magnetosphere, depending on what the wind speed is and what's happening at the sun. So just to go into the basic structure, we've got radiation belts sort of in the center here, in these red areas. Those are going to be greater than 500 keV, electrons and protons. Then we classify a little bit lower energy as ring current in that same kind of co-located area. And then we go into the plasma sphere, which is closer into the Earth, and it's a dense plasma, very dense and very low energy. And then we talk about the plasma sheet, which is sort of out here extending back in the tail, where we have just a few EVs of energy. And these can all be overlapping, co-located. There's not very definite boundaries to them. But those are the basic plasma populations. And so we're going to see how we can actually end up with really highly energetic electrons and protons in this region close to Earth. All right, so focusing in on the radiation belts, which is what I'm here to talk about. These are a very dynamic region of particles that are nominally structured as two belts, or you can think of them as two overlapped donuts, right? Because this is a 3D structure in a torus shape. So we can think of this as an outer donut and an inner donut, where Earth is at the donut hole. And these are shaped by very dynamic processes. There's constant competition between source and loss. And so you get a lot of back and forth, waxing and waning of these particle intensities. And it can be very dynamic on short time scales. Okay, and then just to review the motion of how particles go in this system, we see that we have basically three types of particle motion. And this will be for our higher energies that are really trapped in that magnetic field. So somehow they've been elevated to higher energies, and now they're going to just exist in this magnetic field until something else happens to them. So those three motions are going to be the gyro motion, which is our spiral motion around the field. And you can kind of see that here in this GIF, that spiral motion. And then we have bounce motion, which is you can see that particles going between the reflection points near the northern hemisphere and then the southern hemisphere back and forth. And then that whole thing drifts around the Earth as well, with different drift speeds depending on energy. So that's what we've got going on for each of our particles. They all have these three motions attributed to them. And we're going to try and study those with our Van Allen probes. And so in the next slide here, I'm going to show sort of how those probes go close to Earth and then out away from Earth over and over again, right through the heart of the radiation belts. Okay, now they're called RBSP in this picture because they were launched with the name radiation belt storm probes. But as soon as everything was working correctly, we renamed them to honor James Van Allen and call them the Van Allen probes. All right, so now we've got 7 years of data from going around and around, cutting right through the equatorial heart of these radiation belts. We were launched in fall of 2012 and then decommissioned in fall of 2019. And so there's just so much data here to be learned. And you can kind of see in this movie that one probe is following the other, right? Sometimes they separate a bit based on their orbits. They were meant to do this. So their phasing is off and one might be on the outbound leg while one's on the inbound leg. And then other times they're really closely chasing each other like this picture is showing. Okay, so I'm going to just bring in the Iowa legacy briefly, and then there's a cautionary tale applied to this, which is why I like to talk about it. So this is a picture here of Explorer 1, the satellite that they're holding up there. There's James Van Allen in the middle, Wernher von Braun over here, and William Pickering. And they're holding up the first US satellite that was launched into space. This, of course, got James Van Allen the cover of Time magazine that year. This was launched in January 1958. And the key thing about this mission is that it had a Geiger counter on board, and it was actually the first observations that we had of the radiation belts. And so now you can understand why they were called Van Allen belts. And as Giannis mentioned, I'm fortunate enough to be working in Van Allen Hall, the place where James Van Allen was chair of the physics department for many years and got his discovery made. And so it's very much a privilege and an honor to be working in that same building as James Van Allen, and he built up this space program from the ground up, essentially. Okay, but why is this a cautionary tale? So at the time, it wasn't just Explorer 1 that was in space. So Russia had launched not one, but 2 satellites previous to that. And this pictured here is Sputnik 2, was launched just a few months earlier before Explorer 1 in November 1957. They missed out on the discovery of the radiation belts, and I'll tell you why. They also had Geiger counters on board, and they could have easily seen that data and realized that they were looking at radiation in space. But their transmission of data was not able to be captured at the right latitudes. And so Russia wasn't able to actually downlink the data from space. And it was intercepted by a couple of countries, including Australia. And Australia basically said, hey, if you share us with the decoding process, we'll share the data with you so that we can maybe work on this together in collaboration. And Russia said, no, we're not giving you the code to be able to translate our spacecraft data. And so they didn't give them the data, and they basically never saw that data until sometime later. So what could have been called the Vernov belts and discovered by Russia ended up being called the Van Allen belts because they were refusing to collaborate. So that's just a cautionary tale. It's always good to collaborate with others on scientific discoveries. And so we have the Van Allen belts. Okay, just a little bit of geopolitical history. All right, so back to the data. So this is something that I want to set up first before going into more plots about what we see with the Van Allen probes, because this is a very particular way in which we visualize our data. Now, this is the picture of the radiation belts, but you notice it's kind of turned on its side. So here's Earth down here, and then here's the equatorially symmetric radiation belts that are extending upward. Because what we like to do to show changes in the radiation belts is we like to plot a vertical cut through the radiation belts, going from close to Earth to away from Earth, and then back again, and then line up those cuts over time. So what you get is a plot that looks like this down below. So this basically shows changes in intensity in the radiation belts over time and over L shell. That's what we call L shell, which is the approximate Earth in Earth radii. So down here, you're really close to Earth, and then up here, you're about 6.5 Earth radii away from Earth. And so out here, we consider this to be the outer radiation belt. Down here, here's our inner radiation belt. And then now we can observe the changes that happen in time at different locations. And then if we start to look at different energies, we can really see the full picture. Okay, so now we're going to get into the good stuff. So here's one of those plots that extends from the beginning of the mission, so September 2012, and then each panel is a subsequent time interval all the way until we get to October of 2019. So we've got our 7 full years of data here. And this energy I'm showing is pretty high energy. So this is 4.2 mega electron volts. So this is sort of at the upper range of what we see commonly in the radiation belts, highly relativistic, highly energetic. And what we've noticed, especially with this mission, is that there's almost like different physics that defines electrons at these energies versus when you're talking about lower energies. So you have to think of them as almost a different class of particles. Now, in these pictures, I'm not showing the inner radiation belt, I'm just focused on the outer. So you can see that it's actually clipped off and you're not really seeing anything below about L of 2.5, so 2.5 Earth radii. But there is an inner radiation belt down here. I'm just focusing in on this outer belt. All right, so a couple of things we notice. First thing is we notice a third belt structure at launch. And so we can see there's basically 2 outer belts, right? There's this outer belt and this inner outer belt. And then again, there's the not shown inner zone below that. So we kind of consider that to be a 3 belt structure. So that was something new that we hadn't seen before. It happened right at launch. Then we look through the data and there are other times. So I'm going to point way down here to October, November 2018. This is another good example where we've got these clean 2 outer zones, and then we would have the inner belt below that. So there are definitely other instances of these 3 belt structures. You notice through end of 2013 into 2014, the joke was that the radiation belts lost funding because they essentially disappeared, certainly at high energies. There was just nothing going on for this amount of time. And it was a little bit of a nervous time because we were kind of hoping it wasn't going to stay that way. But then the activity did start to pick up again in mid-2015. And we see what looks like almost repeated patterns, especially when you get down here into sort of summer of 2016 and into 2017. You see these just repeated enhancements that come by over and over again. And this was during the declining phase of the solar cycle, when we have a lot of co-rotating interaction regions. We have a coronal hole that's sort of fixed on the sun, or can be fixed on the sun. And every time the sun rotates again, about every month or so, as that hole rotates back towards Earth, it's going to spew out a stream of particles that will energize these radiation belts. So that's the simple version, but that's what we're basically seeing here is this repeated storm that happens over and over and over again. It's a series of coronal holes that just keep rotating, and as soon as they come back around to face the Earth, you get another enhancement. Okay, so here's a quiz for everyone. Can you guess, looking at this plot, and I just want you to make your predictions, and then I'll show you. where solar maximum and solar minimum occurred. So you may know the answer. So don't say it out loud if you know it, but just in your head, make your guess and say, okay, I think minimum occurred here. I think maximum occurred here, and then I'll show you. 2015, okay. Is that maximum or minimum? Maximum, okay. All right. So there's one guess, maybe around here, maximum. Okay, and then think about where minimum would be. And okay, another guess, 2019 maximum. Okay, somewhere in here. It's really hard to tell, right? Now I'll tell you that maximum and minimum did occur within this time period. So we've got essentially within this time period. So we can see both maximum and minimum, but it really is hard to tell by looking at these highly relativistic electrons. Okay, so everyone's got their guesses in their head. I'm going to reveal the answers now. Solar maximum, right there in April 2014, right when nothing's going on. All right, and then solar minimum, oops. Solar minimum is essentially right after decommissioning. So in November, December of 2019. So not really what we thought at all, right? One of the clues here was that we are in the declining phase of solar cycle when we see these repeated solar storms showing up as particle enhancements. And so this is the declining phase through here. So that would have kind of given you a clue that maximum had to be somewhere sort of before 2015 or maybe beginning of 2015, but it actually occurred right here during this dead spot. You know, that's, this is one of those mysteries, which is why I love studying this stuff, is that these particles are not necessarily directly driven by solar activity, by number of sunspots, by any solar maximum or solar minimum. These highly energetic electrons are really a complex combination of what's happening in the sun and also what's happening in the magnetosphere. And then, you know, there's still stuff that we're discovering about what's causing the enhancements versus the losses. So I just like to make that point. And I will say that this solar maximum is not a typical one, right? It was a low solar maximum. So this may not be what we always would see at solar maximum. This was a historically low solar maximum with a low number of sunspots throughout the entire solar cycle. And the indication is that our next solar cycle will be somewhat low as well. Okay, so now I'm going to get into a few of the fundamental questions that we have studied with these data. So that includes, where do these come from? How do they get around? And then what happens to them? Where do they go? That's basically what you'd want to know, right? If you're studying these particles in space. Where do they come from? How do they move around? And then where do they go? So this movie here is a model. It's not real data. There's been, because we don't observe the entire 3D radiation belts at any one time. We just have one or two single satellites cutting through. So we end up modeling the flux to conform to our donut shape here. But this is based on real data, and it's showing this 3-belt structure that we reported on in 2013. That showed up right at launch. And so you can kind of see now in a maybe more dynamic view how we've got our inner belts down here, but then we've got 2 outer zones. And so we almost have a bifurcation of the outer radiation belt into 2 different belts with a minima between them. So that was pretty new stuff. Okay, so let's talk about where these come from. And before we do that, I need to go over the idea of plasma waves in the magnetosphere. So we don't need to get into the details of all of this, but this cartoon pretty much sums it up. There's a bunch of waves that happen in different locations at different times. and they're all overlapping, and they act on different particle energies, and they sometimes will either energize particles or they may scatter particles along the field line so that they end up lost in the atmosphere. So there's a couple of different things that can happen with the interactions between these plasma waves and the particles. But here we'll point out the two main ones I'm going to talk about that affect our highly energetic electrons are the chorus waves and the ultra low frequency waves. Now we refer to ultra low frequency as ULF, and our chorus waves they're often called Whistler mode chorus when they're in the inner magnetosphere, but technically they are VLF, or very low frequency. So we use these funny ultra low and very low because, well, essentially people kept finding different frequency bands of waves, and we had to go with more and more superlative prefixes here. Okay, the way that we look at these is with our field instruments, which we have on board Van Allen probes. Now, this is a figure back from a different satellite mission, the CREST mission, but it's a canonical figure. Everyone shows it because it has the entire zoo of plasma waves all in one place, where you can kind of start to see there's a bunch here, right? There's a lot of details, and we're not going to talk about most of these. Again, we're going to talk primarily about this VLF, or Whistler mode chorus, and then there's the ULF, or ultra low frequency, which you really can't even see on the power spectrogram like this. So ultra low frequency. Okay, so this gets really complicated really quickly as well. It's kind of fun to dive into the wave data. But we're going to use the wave data to sort of inform our look at the particle data and the changes that we see in the particle data. Okay, so back to our question about where these electrons come from. The idea is what is the mechanism behind this acceleration? And I want you to get from this talk that there's basically two main forms of acceleration. And there's other things that can happen as well, but these are thought to be the two competing mechanisms. Okay, the first one is local acceleration, or the source from the inside of the radiation belts. And this is driven by interaction with our VLF waves, which we saw are also called chorus waves on the last slide. And this is the source that comes right from the inside. So things get accelerated in place. Something is acting with the waves and the particles to produce acceleration or higher energies at that location. So that's why it's called local acceleration. And here's sort of a cartoon about what that might look like, is you have a growing population from in the heart of the radiation belts. Okay, the second mechanism is inward radial diffusion, and this is a source from outside. So this is particles that may be outside of the normal range of the radiation belt distance, and something's bringing them in. So this is also going to be interaction with plasma waves. They're going to bring those particles in closer to Earth. As they come in closer to Earth, they're going to encounter stronger magnetic fields, and some details here that we're going to gloss over, but basically to conserve some of their properties, they're going to energize. So you're going to bring particles in and you're going to increase their energy. And so again, this is different because you're going to see things have to come in from the outer boundary in towards Earth. So inward radial diffusion, and that's going to be driven by ULF waves. So it's really, really difficult to tell which one is the dominant cause of acceleration. Anyone who studied this knows that you often see the VLF waves and the ULF waves happen together instead of separately. So it's important to do very careful study of this and modeling of this. And that's a lot of the research that has been undertaken during the Van Allen probes mission. And it's still an area of active research. And the question has become, under which conditions does one mechanism dominate over the other? So like maybe solar wind wise, right? What's the solar driving that causes the acceleration to be due to VLF waves more so than by ULF waves and vice versa? Okay, so because we get different events that each show evidence of different mechanisms, it's a little bit hard to say kind of which one is dominant. And so the emerging picture, I would say, that has come out of a lot of the the research that has been done is both mechanisms are operating, usually at the same time, and they're acting on different energies. So you can have combinations of both mechanisms, maybe acting on medium high to very high energy, and then very high to even higher energy. And you can have this combination effect going on. And so this is a cartoon schematic that we've adapted from an earlier study. That earlier study was just looking at VLF waves, or what we call chorus waves. But here we're going to see that we can have acceleration by either VLF wave interactions or inward radial diffusion interactions with ULF waves. But the whole thing does still start back with substorm injections, because somehow you have to get a lower energy base population, a source or a seed population there. Then those electrons can get bumped up to higher energies. But you have to have a base, right? If you don't have a base, nothing happens. So you've got to have that base there, and it does tie back to geomagnetic activity and specifically to these substorm injections. And if you want that process to continue on and eventually pump up to outer belt relativistic electrons, you also have to have a replenishment of those source and seed electrons, your lower energies, and keep bringing more of those in to get either accelerated or to grow waves that accelerate other electrons. And so you want to have this somewhat continuous population coming in of source and seed electrons. So this is just the very surface of this topic. If you want more, there's a great review paper by Wen Li, and then there's also some, and that's kind of touches on everything. But then there's some great ULF wave analysis that's been done by Theodore Saris, who I'm sure some of you know, that has contributed to this argument quite a bit. So there's more to dive into if you're interested. Okay, we also have shock-induced acceleration, which happens from time to time. I'm not going to get too much into this, but in this figure here, you can see these bright dots that appear, these bright intensities that come kind of out of nowhere. And this is where we get our shock acceleration. So an interplanetary shock that comes essentially as a solar wind transient hits the Earth's magnetosphere, and we get this sudden acceleration from seemingly nowhere. So this can happen with these interplanetary shocks, and we can get just very sudden, very quick enhancements up to multi-MeV energies. There was a nice study that looked at sort of how often this happens, and they saw that 25% of these shock impacts produced enhancements, and another 14% actually produced depletions. So it can go both ways. You can produce acceleration from nothing, or you can actually kind of get loss or removal of these high energies. But that is one way we can accelerate our electrons. And then the last point here is that substorm injections are really important. And I kind of said that a couple slides ago, but if we look at how the substorms occur in the magnetic field tail of Earth, we saw that movie earlier where you could see sort of energy loading in the tail. And then there's a process called magnetic reconnection, by which oppositely-ish directed field lines can touch and reconnect. And you end up bringing in a lot of flux and magnetic field and particle flux in towards the Earth as it snaps back. And then you have a blob that kind of goes off away down tail into interplanetary space. But there's this one that's coming towards Earth is going to carry with it particles. There's going to be energization mechanisms happening in that process. And then when you get to the inner field lines close to Earth, that's where we get our source and seed populations that can then get bumped up into the radiation belts. Okay, so that's really important. There was a great study that looked at the correlation of different indices, different geomagnetic indices with our high mu electrons or high energy electrons. And I'll just summarize here that basically the higher energies, the highest energies, the substorm index has the highest correlation. So it's not dependent on what we call geomagnetic storms, which are the large scale storms, but it's really more dependent on these smaller disturbances called substorms. Okay, why does that work? So substorms are going to contribute to increases in both VLF waves and ULF waves. And so again, we're seeing this combination of local acceleration and radial diffusion, and we're pumping up those energies. I also want to point you to a nice paper that just came out in 2020. It was like fall of 2020. And some of the authors are on this call, but this one is, again, showing us that this is still an active area of research. We're still looking into these things with all of the beautiful data that we've had from Van Allen probes. And one of the conclusions of this paper is, again, contributing to this argument very nicely, that substorms are very important to this process. Okay, so our next question is, how do these things then move around the magnetosphere? So say they get energized in one place, what happens to kind of move them around? Okay, so we've got inward and outward radial diffusion taking place. So we've talked about inward radial diffusion as particles come in, but we also have outward radial diffusion. And these are often stochastic processes or your random walk sort of processes, where your particles really want to go in one direction or another, depending on the gradient of your density, essentially, of those particles. So in this case that I'm showing here, these particles, when they get little kicks, little perturbations, they're going to tend to go in this direction and following that negative gradient, right? They're going to tend to go to the region of lower population. Rather, some of them will go to the region of higher, but most of them will go to the region of lower population. And so you're going to end up with inward radial diffusion. Over here on the left, some of this area, so out here, greater than L of 4.5, some of these profiles here, you're going to see if one of these particles gets a little kick, it's more likely it's going to go to higher, because it's going to tend to follow that negative gradient. Okay, so these are constant kicks that they're getting over and over again, and it's just a statistical tendency to go to this direction. But depending on the gradient of the population that already exists, you're either going to get outward diffusion or you may get inward diffusion. So that's how we can start to sort of move or see particles move around. Now, when they get out far enough, they can intersect the magnetopause. And that's that boundary between essentially the solar wind and the magnetosphere. And when they intersect that magnetopause, they may find themselves on an open field line, right? Not one of the closed field lines that connect to Earth, but one that's part of the solar wind. And it just keeps going out into interplanetary space, and therefore they are gone from the system. That's how they could leave. Inward, we don't really know what happens to them, right? So we can't say that they leave on open field lines, but we can look at, we'll look at next, how they get lost from the system if they're moving inward closer to Earth. Okay, one thing I want to touch on is the impenetrable barrier. This was one of the sort of new discoveries that came out of the Van Allen probe's mission. And this was essentially the tendency to have a barrier or boundary by which these highly energetic electrons don't really like to cross. And it's when you get close enough to Earth, when you get to the stronger and stronger magnetic field. That boundary can change with time, a little bit closer or further away from Earth, but it tends to be long lasting. And so you can see in some of these cases that you get weeks of time in which you're not really seeing particles come inward any longer. They're staying at this steady level, this steady boundary. You can sometimes have a jump where that boundary goes in a little bit, shifts inward, but then they tend to stay there at that new boundary. So this was modeled as well down here in some assimilative modeling work that was done looking at 2 MeV electrons. And the idea here, the big idea, is that we are seeing that there's this effective barrier almost all the time. And it's basically due to the fact that at a certain point, your inward radial diffusion or your inward push rate tends to equal the rate of scattering into the atmosphere and getting lost. So every time you kind of move inward a little bit, the same rate is going to, at the same rate, you're going to be lost, and you're going to leave the system through the atmosphere. So there's a balance there, and that's going to be what ends up kind of creating this more or less steady barrier. Of course, if you have very strong solar driving, though, you can breach this barrier. So it's not a steel wall; it's more like a wall of dirt. You could punch through it if you had enough strength. But it does tend to be pretty stable unless you have strong solar driving. Okay, so if we look at long-term observations of the barrier, we can actually see that it's again pretty stable, except for a few punctures, what we call punctures, through that barrier at around L3 Earth radii. And so we've looked at long-term POSE observations. Now, POSE is a low Earth orbiting satellite, but it does measure relativistic electrons. And we see that over about 10 years of time, we had at least a couple dozen events. And then in the next 10 years, we had almost none. We had maybe a few. But in the first 10 years, we had about a dozen events, or a couple dozen events. And what we also saw was that this puncture through the barrier was very well correlated with PC5 ULF wave activity from a ground-based index. And so this certainly does point to the role that ULF-driven inward diffusion can play in these types of events here. So we're still looking into that, but this is sort of a new result that we've just come up with. Okay, so our final question is what happens to them? So where do these particles go? They can't just keep increasing, or our radiation belts would just get stronger and stronger and stronger and would never go back down. So certainly they have to get lost from the system, they have to go. And we've seen that, we've already argued that we can lose them towards the outer boundary, right, at the outer point of the magnetosphere. But we can also have loss to the atmosphere. So loss to the atmosphere is going to focus on particles that get scattered, so they follow the field line more closely. And when they end up following it all the way down to a low altitude, like in this box here, they can actually intersect with the atmosphere, and there they can deposit their energy, and they won't recover and execute their bounce motion like we saw in our cartoon at the beginning. So these waves can actually just kind of push them into the right configuration so that they head into the atmosphere, collide, and never come back. So we do have a couple of mechanisms that can create loss to the atmosphere. And then just to point out on this cartoon, again, we can have loss to the magnetopause, and that's sort of out here at this outer boundary. So it's almost like you get kind of pushed inward to the atmosphere, or you get pushed outward to the magnetopause. And the way that looks like in our radial gradients, or our how much density of particles at a certain location. Now for His waves, which we haven't really talked about, you get gradual loss at kind of all L shells. For outward radial diffusion, and that includes sudden compression, where you were on a trapped field line, but all of a sudden the magnetic field has been compressed and you may find yourself on an open field line all of a sudden. That's going to look like this, where you have a sudden drop at high L shells away from Earth, right? So this is very characteristic of loss to the magnetopause. And then there's also this pitch angle scattering to the atmosphere by Emic waves, EMIC waves, some people call. So we haven't talked about those at all, but we will for just a minute, because these specifically interact with our high energy electrons, and they can create loss at a local position. So they deep within the radiation belt, they can create a sudden loss. Okay, and this ties into this mystery of dropouts. We see this quite often in our data, that all of a sudden there's just sort of a blank spot, right? There's a dropout that happens where the flux kind of goes away and sometimes doesn't come back, sometimes does come back, and can be reaccelerated, or you can have an adiabatic effect in there as well. But a lot of other times we will see just a dropout and then nothing recovers after that. So we call these dropout events because they're sudden loss. They're across all L shells, right, all the way into very close to Earth. And this is often when the magnetopause is compressed, and we have this outward diffusion, but we're not really understanding the right diffusion rates because we're still not able to model the correct diffusion rates that would allow for this to drop all of the flux at all L shells as we cut through the entire radiation belt. So there may be something else going on, or maybe we just have our diffusion rates a little bit wrong. The something else that might be going on is the Emic waves, like I discussed. And these are going to significantly affect our high energy electrons primarily. And what we see is when we look at the density essentially of our population, we can see these little local minima, right? Like you see in the right-hand side here. This is not in energy, it's in a different format, but take my word for it, this is high energy, multi-MeV energy. Over here at low energies, we don't see a drop. So this kind of points to the fact that we have these Emic wave interactions. They're only affecting high energies, and they can show a sudden drop at a very specific location. So that's a way we can kind of take a bite out of the donut and get rid of some of these particles really quickly. Now, one of the questions for this that I think is still under investigation in large part is how common is this, right? How often does it happen? Emic waves, they certainly do cause losses at low pitch angles. So this is a little more detail, but as you get to the sides or the tails of the particle distribution, you end up with losses occurring more often at those edges, at lower pitch angles. This is some really nice work by Maria Usanova looking at how Emic waves affect just the outer portions or the tails of the distribution of different energies, but multi-MeV energies, right? 2 MeV, 4.5 MeV, 5.6 MeV. And so we're seeing like low pitch angles getting lost, but not the very middle, not the core of the population. So one of the questions is maybe there's two things working in concert together. So the Emic waves can get rid of low pitch angles, but something else needs to kind of move the particles from the center pitch angles out to the sides. And there's maybe some of that idea going on, but when you look at something like relativistic electron precipitation and Emic waves together, as this nice study did, you see that really there's only a small fraction of Emic waves that are actually resulting in loss to the atmosphere. So one of the questions still is, can these Emic wave losses actually account for a substantial or significant part of our total loss? And we're still looking into that. Okay, so just one more detail here with our outward loss, right? Our loss to the outside of our magnetosphere. So we can have this magnetosphere compression and then outward radial diffusion, and that can end up kind of draining particles away out onto open field lines, and they're kind of lost forever. They never come back. This definitely describes some events very well. We can see through a schematic here, step by step, how this might produce an overall lower amount of particles in the radiation belt from where it started. But we see that to really get this to match a lot of our events, we need something like ring current expansion, where we puff up the ring current essentially so that we move particles outward and the magnetopause comes inward. So therefore we get greater loss than we were expecting. And so just the magnetopause shadowing and outward diffusion doesn't really explain the full emptying of the radiation belts down to low L shells. So it seems like something like this ring current expansion, where things are moving outward as the magnetopause is moving inward, and you have outward diffusion, is really the combination of things that need to happen to get this full loss from the radiation belts. Okay, and then totally different topic just at the end here is solar protons. So I haven't talked about protons at all. In our high energies, we do see solar proton events. And these are like concentrated bursts of protons that get accelerated either on the sun or potentially on their way from the sun to the Earth. And we see them hit our magnetosphere and kind of come into our magnetosphere and show some of the same substructure that you see in the solar wind data out ahead of Earth, we can see some of that same substructure within the magnetosphere. And so not going into this too much, but just to say that we don't really understand how these SCPs access the magnetosphere all the time, because we get sort of different results than what should be true from theory and calculation. So that's a really cool area of open research as well. Okay, I'm just going to end with a summary here. We have observations from Van Allen probes that I would say have fundamentally changed our understanding of this near-Earth space environment. We are starting to look more at event-specific modeling to increase our understanding of the whole system, because parameterizations don't necessarily work so well. Each event almost seems to be different from the next. And depressingly, we are currently left without an intermagnetosphere radiation belt focused mission, at least from the US. The JAXA mission, Japanese Space Agency mission, ARASE, is very nice to have right now to sort of bridge that gap. But hopefully also we're going to have CubeSats take on that challenge. So we've got several of them. The GTO-SAT led by Lauren Blum, the Serbi satellite CubeSat led by Shinlin Lee, and the real CubeSat led by Robin Millen. And those are just the ones that have been funded, and there's others that are being proposed. And so maybe we can start to have more and more radiation belt satellites, just they're going to be a lot smaller. Okay, thank you very much, and I'll take any questions.
Okay, thank you, Allison. So, yeah, the floor is open for questions. Okay, I'm taking note of the new CubeSat missions.
Right.
Aware. Okay.
Yeah, none of them have launched yet, but they're all still in development.
Okay, let me, as I don't see any question, let me ask you, you showed us the influence of EMIC waves just a few slides ago. Maybe you could you go back?
Yeah. This one or this? Oops. Next one?
The previous one. Yeah, here. Okay. Yeah, and you mentioned that it seems that the EMIC waves have an impact on the lower pitch angle particles, right?
Right.
So does this indicate that the particles, that there is that there is pitch angle scattering by the EMIC waves, and which drives the particles into the loss cone? Is this what
Yes.
we think of it?
Yes.
But the EMIC waves, they don't have such a high frequency. I mean, we usually associate this with waves that are a bit higher in frequency and gyro resonate, right? Isn't it right?
Yes. So yeah. So you're thinking of back to those VLF waves, which are really only going to be efficient at scattering lower energies than this. So they're not going to be efficient at loss of or pitch angle scattering of high multi-MeV energies.
And why is this the case?
So that resonant energy with the gyro resonance that you're talking about with like Whistler mode chorus, those interactions are going to be most efficient at about tens to maybe 100 or a couple hundred keV. And so definitely in the lower, sort of in the what we call the medium energies rather than these really, really high energies. They are efficient at momentum scattering or acceleration of these high energies, but they're not efficient at pitch angle scattering of these high energies.
Okay. I had Well, I had the impression that the slot region is being created by his waves, which are they? I mean, they have frequencies in this range, and this doesn't this contradict to what you just mentioned, that they are not efficient in pitch angle scattering those waves?
Yeah, so let me just go back to one of the earlier pictures here, because you're exactly right that the His wave is going to create that slot region, but look at some of these long lasting what we call remnant belts, or low L belts from these high energies that last for months at a time. So his scattering is taking place. This is all within plasmasphere, right? Within, after storm has happened, plasmasphere is definitely pumped up to outside of L3 and a half, but here they last for months because his scattering is so slow at these energies.
Are you showing a picture? Because we don't see
sorry.
it.
Oh, you don't see.
You stopped sharing your slides.
Oh, okay. I thought I just exited slideshow. Okay, hopefully now you see.
Okay.
Okay, let me point again. So these long-lasting remnant belts,
right.
Here.
Mm-hmm.
Here's a good one. These are being acted on by His waves, but it takes sometimes 6 months to really deplete significantly.
Yeah, that's true. It takes a long time.
Yeah.
Mm. Okay, while the EMIC waves are much faster.
Yes. Yes.
Okay. Okay, thank you. Maria has posted a question about the barrier. How are the diffusion coefficients defined? And is there a fundamental reason for having a balance between the diffusion rates at around 2.8, L equal 2.8?
Yeah, so let's see if I can get there. Oh boy, a bunch of stuff. All right, it should be coming up here. Okay, so here I think this plot is the right one to be looking at. So how are the diffusion coefficients defined? So these are actually modeled or simulated diffusion coefficients. They're not directly produced from data. So this is quasi-linear theory, essentially, is where we come up with these assumed diffusion coefficients with some assumed plasma parameters. So definitely it's all a little bit parameterized, or some assumptions in there as well. But for high energies, this is kind of what those diffusion curves would look like. And the important one to look at is sort of when you get this crossover here, and then we're seeing as we go to lower and lower L, what we end up with is showing lifetime on the left here. So instead of diffusion rate on the right, we can look at a lifetime here on the left. And we see that our pitch angle scattering here is going to be significantly lower lifetime than our radial diffusion rate. And so it's almost like every time you kind of get a little kick inward in space, you then get a very quick kick to scattered pitch angles or low pitch angle, and you immediately can be lost by the atmosphere or collide with the atmosphere. So that's kind of what we think is causing that barrier, is just that we have enough of a difference here where this one becomes very dominant, and there's lots of pitch angle scattering and only a little bit of inward motion. I think is the question. Oh, go ahead.
Yes, this was the question, but I was wondering how this depends on the particle energy, because you mentioned this balance happening for high energy electrons at this particular distance. And the other is related to the explanation that you gave, that these diffusion coefficients come out from a quasi-linear theory. So do they depend, I suppose they depend on the magnetic field of the strength of the magnetosphere, but also on some perturbation of the magnetic field. So I don't really understand how these come into play, and if these values are, I mean, if we would go to another planet with a different magnetospheric structure, or if this balance would happen in another
Right, certainly.
distance.
Yes.
Yeah, this was kind of the question.
Right, okay, yeah, that's a great question, because what these diffusion coefficients are going to depend on most strongly is going to be magnetic field at the point, but also density, low energy thermal plasma density. So that density can change certainly with time, and so these are again just modeled diffusion coefficients. And so the hypothesis is that this is kind of the process that is taking place. And because there's such a difference in diffusion rate, we just don't end up seeing anything that can kind of cross over that boundary. But it's possible that event by event, and we see that when we look at our data, that sometimes this barrier becomes lower, right, for some amount of time. And this is due to this fact that things are changing and it's a little bit dynamic. And you're right, if we go to, say, Jupiter, where magnetic field is much stronger at the same equivalent distance from Jupiter as it is here at Earth, then we are going to see a very, very big difference here in diffusion rates. Although we see some of the same wave modes occurring on Jupiter. So it could be analogous, but maybe just different rates.
Okay, thank you.
Any other question for Allison? I see a question here. Are the two outer Van Allen zones always split, or do they ever merge? Because we usually treat it as a single belt.
Yeah, yep. Right. So that's a complicated question because it really depends on energy. There's kind of slow change as you go from these high energies, which I kind of said are maybe need to be thought of as separate physics than lower energies. As you go to lower energies, and I don't think I have a good view of that in my slides, I can look, but as you go to lower energies, this so-called slot region becomes less obvious, and usually not even a slot at all. And it's just like a continuous population of particles from low L all the way up to high L, at least some of the time. And so, yeah, I don't have a good picture of low energy, but it just doesn't really look like you have a defined slot region there. For high energies, we see that in the inner zone, you don't actually usually have anything above about 2 MeV or 2.5 MeV of energy. It's very, very difficult to get particles down that low, especially with our lower solar driving that we've had this solar cycle. So in fact, we don't even usually see an inner zone for these energy electrons. We only see the outer zone. And sometimes we see two outer zones and they end up merging together. If we go back to the summary picture.
We don't see your slides, Allison.
Yeah, hold on. Yeah, if we go back to the summary picture again, glad I put this in, you can see how sometimes it looks like the two outer belts kind of end up merging together, or there's loss at one location and there's not loss at another, and so you end up with kind of back to your nominal single belt eventually.
Yeah, I think that I don't think that there is an agreement on how we have this double outer belt yet.
No.
I think that I know there are some strong disagreements about this.
Yes.
Okay.
That's what makes it fun.
Yeah.
Did someone have their hand up? I thought.
Yes, it's Christos Katsavrias.
Oh yeah.
Christo?
Yeah. Hi. I just wanted to ask you, you talked about a correlation of a substrom index with both VLF and ULF waves before. So does that really imply a common driver? Perhaps? I had in mind something like high-speed streams or something.
Right, exactly. So certainly if you look at like a parameterization of waves, you'll see certain solar wind transients that more often lead to ULF waves, some that more often lead to VLF waves. And mainly I wasn't trying to show correlation with wave mode specifically, but just to say that both can get increased by substorm injections. So you can have ULF waves that are actually directly triggered by injections, by particle bundles coming in and depositing into the inner magnetosphere. So you can have sort of night side ULF waves kicked off from that process, as well as from the day side driving of the solar wind at the day side magnetopause. So you can have a lot of different reasons for these ULF waves, and they just tend to increase. If you look after storm after storm after storm, you always see like PC5 power increase. At the same time, you see VLF power increase.
Okay, thank you.
Was that your question? Or what,
Yes,
can you rephrase your question if I didn't answer it?
No, it was fine.
Okay.
There is one more question. Can we see at the wrapped diagram at some point both outer inner belts and the slot at the same time? I assume that what Aris is asking is whether the Van Allen probes have ever detected electrons at the same very high energy, both in the outer belt, slot region, and inner belt. But I think you just said before that in the inner belt, the highest electron energy that we have ever recorded is something like 2 MeV. Was that right?
Yeah, in this solar cycle. So during the Van Allen probes mission, right? Yeah. So it's a little more complicated, but we do see signal down here below this level below LF2. We see signal, but it's actually due to contamination by the high energy protons that exist in that inner zone, and they sort of masquerade as electrons. We've done some careful analysis, and we found that we don't see electrons of greater than 2 MeV down there. There may be a few, but our sensitivity is not high enough to see if there's only a few, and if there are any, it's a very, very small amount.
Yeah, I am aware of the contamination problem in the inner belt. So we do not really know, do we? Because of this contamination issue.
So yeah, we can do things like look at the pitch angle distribution down in the inner belt. And if it were an electron distribution, you'd expect it to be trapped radiation. And instead we see a flat distribution. So all pitch angles equal level, meaning that we actually are looking at particles coming in from all directions behind the instrument, side of the instrument. And this means that they're high energy protons that kind of can get through the shield, and they end up showing this flat distribution. So we are sure that we are seeing mostly protons. If there's any electrons, again, they're just so low that we're not able to even observe them with our instrument.
Okay.
Yeah.
So if Ari, if this was your question, we probably cannot see at the same time very high energy electrons at all these areas.
But go back a few years and look at some of the earlier missions, SAMPAX or CREST, and you do see at times an inner zone at the same time as slot region and outer zones. Yeah.
Okay. Fine. Okay. I don't see any other question. So that was a great talk. Thank you very much, Allison, for being with us. I very much enjoyed it. And
yeah, thanks for having me. It was great to see some of you virtually.
Hopefully, yes. Hopefully soon.
Yeah. Thank you very much, Allison. Yes, it was very interesting talk, even for the non-experts like me.
Okay, stay safe.
Yep,
and,
you too.
Well, hope to see you at the latest, hopefully during COSPAR next year.
I will plan on it.
In person. Okay.
Okay.